Okay, so good afternoon, everyone. So we shall start our class 30 in. I think one more student to, I think two more students to go. Okay. Anyhow, we can start first. Okay. Perhaps I will give you all a fast recap. So now is we are in chapter 2, which is more on the as I mentioned before, for this course we will focus in three different uh, field. The first one will be image processing, followed by audio and also video processing. So whatever we learn in image processing is applicable to video processing because I already mentioned before that the video is actually a series of image arranged in a correct sequence. So all the images arranged in such a sequence we know it as a frame. So we have FPS, frame per second. So basically, all the image processing applicable to images is applicable to video as well, because we will process the video as an individual image. So as I mentioned before, we have an image is actually a 2D signal. So this 2D signal would be characterized by X and Y. The horizontal X and the vertical Y. So basically, this is 1D signal. This is 1D signal. So add up together, you have a 2D signal. So basically, an image is actually you can actually portray the image as a Cartesian plan. So each and every pixel, it will give a coordinate such as 0, 0, 1, 1, 1, 2, something like that. Okay, so pixel would be the basic elements in an image. So we also call it as a picture element, but most of the time we call it as pixel instead. So we have three different kind of images. For example, we have grayscale, true color, and color map. So basically, grayscale is actually, grayscale is from 0 to 288, 0 to 255. So which means the intensity, this is the intensity value. So 0 would be black color, and 255 would be white color. So the rest of the color ranges between 0 and also white would be uh, gray color, uh, either light gray or dark gray color, depends. Okay, so if let's say you have RGB image, so you have R, the value will be 0 to 255, G, the value 0 to 255, and B, the value 0 to 255, the same thing. Okay, so for RG and B value, it is actually overlapping, superimpose one another. You can see the image as something like this one. So three image superimposed together. So in MATLAB, you would able to get something like, maybe let's say the R value is 100, G value is 200, and B value is 255. So perhaps you will get 100, 200, 255, something like this one. Okay. Usually in most of the software or most of the image processing tools, the first one would be referring to R, second one will be referring to G, and the last one referring to B, which is red, green, and blue channel. And by combining this RGB with different ranges, 0 to 255, for R, G, and B, you were able to get all the color, uh, whatever color we seen. Okay, basically dark blue, light blue, very dark blue, or maybe light red, maroon, and etc. Different kind of color is actually combinations with different values from R, G, and B. Okay, so basically, grayscale image would be 8 bit lah, 2 power 8. Okay, so 2 power 8 would be 256. And why it is 256, but in fact we have only 255 because we have assigned 1 bit for the zero intensity, and the rest 255. So 255 plus 1, which is 256, but 1, which is the zero intensity, we will get 256. So basically, for true color, like the normal RGB image, we will have 24 bits because you have 3 layers. So 3 times 8 will be 24. And something special would be the color map. So color map is something I would say not so common to the public and eventually to you all, because color map is a color image, but in fact it is still 8-bit. Why? Because it only store the data using the index value. So this is an example using the index value. So this is an example using the index value. Basically, this one is the index value, which is 5, and then it will provide you a sort of color map. So you will have to look into the color map and find the data number 5. 1, 2, 3, sorry, 1, 2, 3, 4, and 5. This is number 5, and get this value. Okay, so this will be the value for red, green, and blue. Red value, green value, and blue value. Okay, so basically this would be your value lah, 0.2902, 0.0627, and 0.0627. Then later on, you will get something like this one by using the index 5. Because it is using only 5, only one, I mean, uh, store only one digit, so it will require 8-bit, which means you do not need 3-bit lah, because each layer you need 1 bit to store. So basically, 8-bit for R, 8-bit for G, and 8-bit for B. So total normal image, normal color image should be 24-bit. And for the true color map, for the index image, you only need 8-bit because only need to store the value of index value. Okay. So let us continue in image quality. So as the bitmap image are resolute, another thing would be bitmap and also vector image. So bitmap image is very useful, especially for image processing. Let's say you want to train a model, using deep learning and etc. No matter what model is it, YOLO 4, YOLO 8, and etc. So usually we will pre-process let's say the input image is let's say the input data is images data lah, okay, not numerical data or any other data. So you have to pre-process the data by maybe turning the image, transform the image, scaling the image, and etc. Because for deep learning, will always need a very high number of training data in order to get a promising result. Else, you will not able to get a promising result, because the learning model is exactly like human. Okay, if you want to be knowledgeable, you have to learn more and more. For example, a doctor, he or she, maybe a doctor, he is doing the grading of breast cancer. So let's say he's very new, such as houseman. So perhaps he or she will not so familiar with what features to see, what features to look into, what features is prominent to relate to the standard and etc. But if you are very experienced, let's say you already work for 10 years with a specialist or a master in the histopathology, so perhaps it would be very easy for you to identify. Once you see through the slide, you don't need to refer to the guidelines, you don't need to refer to the protocol directly. You can say, oh, this is what because of this and that, this and that, this and that. Something the same thing happened to the deep learning. So you need to give a lot of images for the deep learning image. For the deep learning model, and then the model will then accept it as a learning processor. So after learning, it will link between the relevant features and will give you a high accurate result. So that is what deep learning is doing. So for that one, we usually process using the bitmap image, and in most of the time, we are actually dealing with bitmap image. Okay, we seldom use vector image. what would be the main application of vector image? It would be the application that you mm, don't want any image processing method which will affect your quality. For example, you want to use sort of a logo, you want to print your logo on a poster and etc. But when you scale up and or scale down the poster, I mean the size of the poster, maybe print from A4 uh, to A1. So basically enlarging or scaling up the image will enlarge the pixel itself. So by using a vector image, so by scaling up and scaling down, you will not affect any of the image quality. So that is why people will usually save all the documents, all the figures in vector format for poster presentations, for any logo, printing white or advertisement and etc. Okay, so that would be the two different types of image. So image quality, as the bitmap image are resolution dependent, the bitmap, this is most of the time, in this course, we will focus only in the bitmap, okay? Because we are dealing with image processing. Image processing only perform on bitmap image. So the bitmap image are resolution dependent, and the image quality is determined by resolution and color or bit depth. So resolution refer to the number of pixels in an image or measurement of output quality of an image. So as I mentioned before, basically the higher the resolution, the more the pixel it has. Let's say you have a HD TV and also a UHD TV. UHD TV would have higher resolutions. By means, it will have a higher number of pixels because you have more pixel to illustrate fine details and etc. So that is why you have more pixel in high resolution stuff lah. Okay, no matter uh, PC, monitor, TV, and etc. So screen monitor resolution. This would be the measurement method we are using. For screen or monitor resolution, we will use PPI, but for printing, we will use DPI. Okay. This would be very common to those that are involved in publications. I'm not sure if you did involve in publication for journal or conference paper, but for the publications, usually the journal or the conference will state that the standard image quality, okay, usually would be 300 dpi, because although the journal is an online journal, but usually most of the time the journal would have print copy as well, and they want to secure the image quality, ensure the image quality is not that low, in case they meant to print the uh, full length article or review paper or whatsoever. Okay, so usually they will ask for 300 dpi. Okay, this would be a very I wouldn't say this is a solid rules and regulations, but usually the common practice would be 300 dpi. If you can provide more than 300 dpi, it's good. But if you provide less than 300 dpi, you will find that the quality of the image, especially on printed page, would be a bit smeared out or blurred. Okay, if your, if your the figure is not that, the fine texture in your figure is not so important, then should be fine. But let's say you have a very fine graph, different line in the graph intersect with one another, and then your resolution is only 100 dpi, let's say. So when the material, the figure is being printed out, perhaps you would be hardly to differentiate between all these intersection points. So that is the common practice, usually 300 dpi. Okay, but anyhow, the way the image quality being measured in the printed papers or printed material and the monitor or screen, which is digital material, would be different. Because in digital, we do not have dot lah. Okay, we use pixel per inch. So inch would be the regular standard, I would say standard measurement, either pixel per inch or dot per inch. Okay, in real, printing industry, actually all these images, I mean all the color image is actually print using dot by dot. Okay. So basically 300 dpi, which means in 1 inch, 1 times 1 inch, you have 300 dot lah. Okay. This would be 300 dpi. Screen and monitor resolutions. When a digital image is displayed on the computer screen, its size is determined by three factors: screen resolution setting, screen size, and also the number of pixels in an image. So uh, these are three factors or the three bottleneck which would affect the image quality. So of course, if you have a very large screen, for sure and you click on full screen, you would expect your image would be distributed throughout your screen, right? This is a not very, very common practice. I believe you all, very aware of this. And then later on, it depends on the screen resolution. Because although the screen size is bigger, not all screen is HD. For example, you have a 49-inch TV. Not all 49-inch TV is HD or UHD. If you are comparing 49-inch TV, which is HD and UHD, you will find that UHD is much more clearer because both TV are having the same size, 49-inch, but in fact, the number of pixel in UHD TV would be much more higher than the HD. That is why, although both both the TV size would be the same, but then the resolution, the texture, the fine texture, the image quality, the contrast is different. Okay, and the other one would be the number of pixels in an image. So if your image only have 9 times 9, sorry, 3 times 3. So total nine pixel only lah. So when you enlarge this one to fully distribute throughout your pixel, you will find that it will become a blocky field. Why? Because all these pixel will be assigned to the same pixel as this one, and all these blocks will be assigned to the same pixel as this one. So this is how the image being distributed. So in order to have a high quality, let's say you play a drama or movie, you must make sure that these three things will be compatible to each other. So let's say you have a very high resolution setting, very high, very big screen, but you have a low number of pixel in your image. You cannot expect a high HD, a full HD or ultra HD display. Screen monitor resolution, PPI, pixels per inch, is a measurement of how many pixels are displayed per inch on the screen. So as I mentioned before, per inch, let's say this is 1 inch and 1 inch. So how many pixels in one times 1 inch, which is a square box. So the more pixel per inch PPI on screen, the finer the texture and hence the better the image quality. On a given monitor, change screen resolution, change the number of pixel of size and size of pixel used to display objects such as icon, text, button, and image. Okay, so changing the screen resolution would change all these lah. Okay. A monitor may be specified as being a low resolution, medium, or high. So basically, this would be a standard protocol to define low, medium, and high. Screen or monitor resolution is measured and proportion standard of width or horizontal height of the pixel. So width or horizontal height or vertical is the same. So this is a very common screen, horizontal and vertical dimensions. So for this horizontal, you have 1,300 pixel, and vertical, you have 800 pixel. So as screen resolution of 800 times 600, the Photoshop and the image being added fill the screen. So when the screen resolution is increased to 1024 times 786, so the image is smaller because the size of the image is remain the same. So you would expect a small size, okay? Uh, at a higher resolution, 1280 and 1024, the image become even smaller, okay? But yeah, so this is how, because the distribution of the pixel is limited. When PPI of resolution increase, the final image details can be obtained. When PPI of screen resolution decreases, the details of the image is reduced. Okay, this is same as the sunflower example. So when you have a higher resolution, the details, the petal, the shading of the sunflower can be very can be easily seen. Okay, can be easily seen. But when you have a very low resolution, you will only see the bloggy image, and when the resolution is too low, you cannot even prescribe the information or what is inside this image. So this is a common screen resolution setting. So the number shows in the table below are the PPI for each combinations. So let's say for the inch, you will have 46. So how you get 46 is actually this would be the resolution 64, I mean 640 divided by the inches, you will get something like this. But because it is a pixel, you cannot have a floating value, which means plot point something else. So you need to uh, convert it round off to become an integer. So that is 46. Printing resolution. As I mentioned before, the monitor display would be in PPI, pixel per inch, but for printing, you will be talking about dot per inch, in which how many dot in 1 inch. So DPI is a measurement of printer resolution that defines how many dot of ink are placed on the page when the image is printed. So this would be the dot and how many dots in 1 inch of image. So used by the printer to describe spacing between the pixel when the pixels are printed out. Okay, the DPI would be remain the same throughout the entire image. It's impossible for, to have, this one is 300 DPI. Suddenly, this block only have 100 DPI. It's not possible. This is how DPI is actually the also telling the user or the manufacturer um, the gap of the pixel itself. So the distribution of gap will be remain the same throughout the entire image. So it's impossible to have 300 dpi here and 100 dpi here and maybe 200 dpi here. It's not possible. Again, the higher the printing resolution, the better the image quality. So let us assume this all this is dot. So this would be 1, 2, 3, 4, 5, 6, 7, 8, 9. So supposed to be 81. 81 1, 2, 3, 4, 5, 6, 7, 9. Okay. 81 DPI. So this is much more higher and higher. So of course, when you enlarge this one to a very high scale, you can see actually it is combination of dot lah. Okay, just that because the dot are closely located, so you cannot see the gap. But for this one, the gap is very obvious. You can see white color gap between the pixel. But for this one, because it is too small, our human eye cannot aware that small details. So that is why we are not. We cannot see any white line, white gap partitioning all these pixel. Color and bit depth. Measure in bit per pixel, number of colors supported, the range of color available for pixel, number of colors supported. Okay, basically, bit per pixel, 1 bit per pixel, image type will be binary because it's only have 0 or 1. And grayscale, you have 0 to 255. High contrast, you have better, and true color, you have 24. Okay, so this will be the example lah. Uh, facts which is the using the binary, but do not confuse. Eventually, binary and the grayscale is two different types of image. Of course, when you have binary, your pixel value will be either 1 or 0. Okay, but for grayscale, you have 0 to 255. Let's say you have a grayscale, but in the entire image, you only have 0 or 1. Okay, 0 or 1, 0 or 255 lah. Okay, which means you have white or black color. um, let's say the entire image you have only this one. You are still occupying the, 8-bit. Why? Because 255 is 8-bit. Okay, because the allocation for this uh, each and every pixel is already allocate 0 to 255. No matter you use or not using it, no matter the image is either black or white, solely black or white, or with gray color, the bit uh, of the image is still 8-bit because for each pixel, it's already assigned 0 to 255. Just that the way you assign would be the same. So let's say you have a binary 0 and 1, and then you have another grayscale 0 and 255. Both the image will look exactly the same. Only fully white or only fully black color, that's all. But actually the bit using here will be 1 and 8 lah. Okay, say your application is only require black and white, binary black and white. You don't need any shading from 0 to 255, then you can opt for binary image, which is require only 1 bit lah. Okay. Image storage size. Image size will increase when the resolution and color depth increase. This is very common because when you have one car, you don't only need one car park, but you have 10 car, you cannot park all the 10 car in one car park. You need 10 car park. Okay, so this is a very common sense, I would say. So basically, if you download a movie and the movie is like HD movie, you will not expect the movie will occupy only maybe 1 MB or maybe 100 KB is not possible. For sure, that one is just buffing you like it is not high HD lah. Okay, let's say your movie is like 2 hours. It's impossible to have 1 MB or maybe 100,000 KB. Okay, because the image size and is always proportional. I will not say directly proportional, but proportional to the image quality. As long as the image quality increase, the image size would increase as well. So image size will increase as the resolution and color depth increase because the more the resolution, the more the pixel value it has. So the more the pixel value it has, the more the information it needs to carry and the color depth. So if you have binary, you only need 1 bit. But if you have, if you are, the image is the grayscale, you need 8-bit, and for the true color, you have 24-bit. So image size is actually the number of pixel times the color depth. This is the way to calculate the image size. So, but please remind that 1 byte is actually 8-bit, and 1 kilobyte is actually 1024 byte, and 1 mega would be 1024 kilobytes. Okay, it's important for you to know the relevancy between 1 byte and bits. And kilobyte. In order to convert a byte, X byte to kilobytes, make sure you do not just simply divide by 1000, but 1024. Okay, because this is relevant to the number of bit as well. So don't misunderstand with the common mathematic practice. When you want to convert meter to to km, then you just simply divide by 1000. Is incorrect here. So 1 bit per pixel for black and white, 8-bit per pixel for grayscale or color map, and 24-bit for true color. So example, the following image with resolution 100 times 50 and color depth of 8-bit. Calculate the resulting image size in byte. So when you see sort of, color image, but it is 8-bit, either way, usually this is referring to this one color map. Okay. Because usually most of the time, if the image is black and white, and it has 8-bit, so perhaps it is a grayscale. But if it is black and white, it's only have 1 bit, so it is a binary. And let's say it has a gray level, maybe something, the pixel intensity, something between black and white, which is maybe gray. So for sure it is a grayscale. And let's say this is a color image and this shows 24-bit, so perhaps it is a true color image. Okay, sometimes the question will not give you so direct oh, this is a true color image with 24-bit per pixel. No lah. Okay, you have to retrieve the informations by reading the question yourself. Okay, so the following image with resolution 100 times 50. So the first one would remark the horizontal pixel and the second will be vertical pixel. So 100 times 50. So with a color depth of 8 pixel, 8 pixel per bit, calculate the resulting image size in byte. So always remember this one. What it is? Oh, okay. So this is the formula, image size equivalent to number of pixel times color depth. So basically it is very simple. So since your resolution is 100 times 50, so 100 for horizontal, 50 by vertical times the color, bit per pixel. So you have sorry, not the bit per pixel, but color depth. So 100 times 50 times x, so you have 4,000, 40,000. Okay. And since it is, I mean, usually the answer should be in byte. So for the 40,000 divided by 8, because you want to convert bit to byte, and then 500 bytes you want to convert to kilobyte, so divide by 1024. So which means you will get KB lah, or maybe you can write kilobyte is fine. But to be frank, whatsoever calculation in, I believe in all the engineering, especially in engineering field or eventually the mathematics, if you did not provide a correct SI unit, um, basically it is a wrong answer lah. Okay, because if you just give me 4.8828, basically I will not give you a full mark. Okay, again, if you provide me a wrong, unit, I will not give you a full marks. Okay, and I will check through the workings. If some part or some portion of the working solution is missing, for example, you only given this one and you directly give me this one, so all the marks between here would be would missing lah. Okay, so make sure you show step by step. Okay, because I'm not sure how you get this one. Can I start at 5,000 bytes? Depends on the questions. Okay. If the question asks for kilobytes, then of course you need to calculate until kilobyte. But the question did not mention anything. Perhaps you can stop at bytes. Okay. But I will because the question is the size in byte. It's fine for you to stop at byte. Okay. No issue for that. Example 2, the following image with resolution 318 times 400 and color depth of 8 bit per pixel, calculate the resulting image in byte. So this would be the byte. I mean, the calculation in byte lah. I believe this one, I mean, maybe the scope is a bit different. I mean, a bit new to you all, but I believe this is a very simple calculations. Okay, perhaps take 2 minutes to calculate this one. Just to play around with the calculator, at least you try. Okay, 2 minutes. Okay, I think 2 minutes is too much. Okay, let us continue. So basically this is how it is being calculated. I think the most important things is that you need to know 1 byte is equivalent to 8 bit, and then 1 kilobyte is actually 1024. Um, a common rules in image processing. Can we say byte is equal to resolution? No, because the byte is usually referring to image size, the size of the image itself, but not the resolution. Because whenever you mention resolutions, it is about this one. Always maybe 100 times 200. So you would expect to have, 100 pixel in horizon. If 100 times 200, then it would be other way, something like this one. Okay, the first one always the horizontal pixel value, the number of pixel, and the second one always the vertical. So is resolution is an important information to calculate the bytes or the image size, but resolution is not equivalent to image size or bytes. Okay, and bytes is only the SI unit. I'm not sure is it SI unit, but at least it's a unit lah. Unit for referring to image size or any file size, maybe audio, not restrict only to image, but maybe audio, video, and etc. Okay, so do not confuse with resolution and the bytes. Okay, always remember this one. So I put in as a note over there. Because in examination, we will not provide this one because all these are not formula. Okay, you have to remember it. If you cannot remember it, then bye bye. Okay, so but don't worry, all this simple calculation. I mean, I'm not the one who um, pass you on your memorization, but you have to know the working principle behind something. Because at the end of the day, when you explain to customer, a customer would ask you, oh, please define Ohm's law. Customer would ask you like that, okay? But in fact, when you're trying to explain something to customer, I mean, when you're really working in industrial, so you have to know the working principle behind uh, some algorithm, some common algorithm. I would perhaps look into, to evaluate eventually in examination, assignment or practical, I would actually want you all to relate what you learn in real, practical work, what is happening in practical work. Because I've been work in practical world, engineer life. Um, Sometimes the graduates is not able to answer something which is eh, that you need to think lah. For example, if you have a if you have if the machine snap an image and the image is in bitmap, okay, full size bitmap. So one of the engineer, the customer lah, go and convert the bitmap image. Uh, okay, maybe I put it like this again. If you have a AOI machine, automated optical inspection machines, so the optical machines would be perform all the inspections. Let's say you have this one, you have a crack here. You have orientation pin 112, your matrix code. This is a common layout lah. Okay, not always the same, but common layout. But you have defects over here, which is a crack. Okay, so during the process, the customer use your machine to snap the image of this one, snap the image of this one, and perform the uh, uh, defects inspections in bitmap, BMP. Okay, and found that, oh, there is a defect over here, and the defect value is maybe 100 micrometer. Okay, and then later on, the customer save this image in JPEG.jpg. Okay, and then we inspect, found that found that X value. So based on your thinking, do you think both this value would be the same? So this is exactly what I expect from you all. Okay, I will not expect please define raster image, please define bitmap image. I will not looking into something like this. But if of course if you are in first and second year, perhaps you will expect this kind of questions appear in your final exam. But for fourth year last semester, I would expect something that you can correlate. Okay, I will give you situations, and of course the situation would within your scope lah. Okay, I wouldn't ask something from the marks, something from this and that, no lah. Okay, and then from there, I will give you a situation like what I mentioned just now, and then I would expect you to give me answer and justifications. Okay, of course, some part may involve calculations, okay, but the marks given is not that high, okay. I don't expect you to calculate, to memorize, Of course, I hope you all do know, but I wouldn't give high marks in those calculations, okay, because later on when you work in real life, you can always Google. It's fine. Okay, I don't know what is 1 by 2, how many equivalent, how many bit. You just Google it. It's fine. The customer will not say, oh, this you cannot Google when you talk to me. No, no, no. You can always Google it. You can always source your information, but not all the time you can source all this background theory, okay, and justifications. So justification would be something that I look into. Okay. So same thing. You have resolutions, you have color depth. So 318 times forward, horizontal, vertical at 8 bit. You get this one divided by 8 bit because 1 byte is equivalent to 8 bit. And then divide by 1024, and then you will get this one. Okay. Oh, another things would be during the examination or the assignment or practical, always give me 4 decimal place. Always 4 decimal place. I'm not sure how what's the requirement from other lecturer, but for me, I always want 4 decimal place. Okay. Uh, uh, Eventually, when you calculate all those, for example, you calculate from the first one until the last one. Maybe perhaps here you will get uh, many different kind of decimal place, right? Please include 4 decimal place to do computations. Okay. Um, why I ask for 4? Because 4 would be a very good um, standard, a very good standard to maintain the sensitivity of your calculation. Let's say you only take 1 or 2, 1 to 4.2, and then you continue calculation. If your calculation is very lengthy, perhaps at the end you will have a discrepancy more than 10%. Okay, so I don't want to have such discrepancy. Okay, so perhaps you need to give me the decimal place in 4. Okay, and I would advise you during the calculations within the solutions, use either the full decimal place or at least 4 decimal place. Else, your answer would be, will have high discrepancy with the answer sheet. So it is difficult to increase or decrease the image size without sacrificing a certain degree of image quality. So we will look into this one in the subsequent chapter, I believe in chapter 5 or chapter 6, during image compressions. Okay, because image compression is a very routine work that we are actually using. I'm not really sure that you are aware or not. Actually, the JPEG is part of the compression method. Okay, JPEG is part of the very important and very cliche compression method, which is using nowadays. Okay, so when you try to compress something, for sure you need to sacrifice something, right? Because for example, you want to, I have only 2 car park, but you have 5 car. For sure, you either want to buy more car park or you sell more car. That's all. Okay, either way. Buy more car park, which means you need to have more storage to compensate the image size you have. Either way, you need to sell your car because you only have 2 car park, right? So you need to sell 3 cars. That's all. Okay. When the size of bitmap image is reduced through a software resize command, some pixels are thrown away. So whenever you use the, for example, in MATLAB, you use im resize it, okay? So whenever you use IM resize, either you scale up or scale down. Whenever you scale up, it will add something, arbitrary pixels to your original image. And when you scale down, it will remove some of the some of the pixel in your image. So it is depends on your applications. For scaled up, it will add in some random. I mean, not really random lah. For sure, when you scale up from when you when you scale up from image maybe 10 times 10 to 100 100 times 100, perhaps you will have, this is very high resolution, maybe an apple. And then after you scale up, because you have extra many pixel, right? 100 times 100. So your apple would be still there, but a little bit blur, because all the pixel, I mean, the fine texture is being uh, disperse out. Will become a blocky feel. Your apple should be in very sharp edges here. Maybe later on you will have a blur apple, but you still can prescribe it as an apple, okay? For all the extra pixel over there. It's impossible for you to scale up an image, and then an apple, suddenly there's an orange beside here, banana here. It's impossible, something like that. Okay. So but of course you would expect additional pixel in, but the pixel is relevant to your original input image. Okay. The another thing would be scale down. When you scale down, maybe you reduce from 10 times, 100 times 100. Oh, sorry, to 10 times 10. So you already remove many pixels. So when you remove many pixels, the algorithm will select some of the pixel to thrown away. Okay. How the pixel is being selected and etc. we will learn later on, perhaps in chapter 5 during the compression. Okay. And this is very important, to select which pixel to be thrown away. Okay. We are not simply just okay lah, mini minor more you, I will discard you. No, no, no. We are not going to do so, but we are actually explore the limitation of human being. Okay, because our human eye can is not sensitive to I mean, high frequency information. So eventually the high frequency information being removed, we will still able to interpret the image. For example, you have a high definitions HD Apple image. Okay, after you compress it, maybe 10 to 1 perhaps, so you will still able to tell that, oh, this is an image, an apple inside this image. You will not, at least you still can interpret what information within uh, this image. Okay. But when it is not possible for you. After compressions, you will say, "Oh, this is not apple lah. This is banana." That is not. It won't happen lah. Okay, don't worry about that. But for sure, when you have a high resolution or high definition apple, after the compression, you might see that this is still an apple, but then the apple is very blur lah, or the edge, or the fine texture, the water droplet on the surface of the apple, the wax, the shiny wax is not visible. But you still you're still able to tell, oh, this is an apple. Okay, so this is what is being the pixel being selected to be thrown away during the process. So when the size of bitmap image is increased through resize command, the software has to create new pixel. This is what I meant by scaled up. Scaled up. Okay. When creating pixel, the software must estimate the color value of the new pixel based on surrounding pixel. Okay. So which means the algorithm would forecasting or estimating what would be the possible pixel. So that is why whenever you scale up your image, you might see a blur image as well, because the fine texture is being dispersed out to form more and more so-called the forecast pixel. So this is what happened during scale up, especially when you scale up significantly, like maybe scale up for 10 times, then you will you expect this kind of blur pixel happen. Okay, but for sure you will still able to interpret the message within the image. After you scaled up an apple image, it's not possible for you to say, oh, this is a banana. It's not possible. Okay, so the process is called interpolation. I believe interpolation is part of the let me recall. I think interpolation is part of the common calculation in statistics, especially important for chemical engineering, I think. So example 3, Calculate the size of the grayscale image if the image dimension is 512 times 512 pixel. So which means this is a square image. Repeat the calculations. This is 24-bit color image. So for the first one, did not mention the bit, but when it mentioned grayscale, for sure it is 8-bit. Okay. So you don't expect this one is being table in a spreadsheet for you to check. Oh, grayscale is equivalent to 8-bit. No, you have to know grayscale is equivalent to 8-bit. Okay, and 24-bit color image. So the same equations, basically 8-bit. So 512 times 512 times 8-bit grayscale. So you will get this one divided by 8 because you want to convert to byte, and then you will divide by 1024 because you want to convert to kilobytes. So that is kilobyte. Stop me if you have questions, or maybe put in the chat box is fine. Okay. I did not really let you all to do this because I think this is very simple. Let me know if you think this is not simple, or if you have any doubts, any confusions, please let me know. Okay. If not, because I cannot see your face emotion, I'm not sure if you are, very confusing with what I teach, or very confusing or disagree with the data or the lecture notes. Is fine. Okay. Let me know. Okay. If you found that anything different from what you learned before, let me know. I will confirm you the data later on. Okay. I'm still learning as well. So image size, the same thing, but this one we calculate using 24-bit lah. Okay, 24-bit true color. So 512 times 512 times 24. Sorry, this is wrong. Should be color. Okay, should be color. Okay, but nevertheless, I already update this one in your in the Google Classroom, so should be no issue lah. Okay, when you refer to the slide in the Google Classroom, I already amend this one. So again, divide by 8-bit and divide by 1024, you will get 768 KB. Okay, make sure when you divide, you don't use the wrong unit. But of course, if it is integer, so you don't need to put zero 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 lah. Okay, if integer, you can omit this one. So example 4, suppose you have captured an image using a 2-megapixel digital camera, which create an image with 1002 and 1006 pixel resolution. What printing resolution should be used if you want to print the picture at the size of 4 times 5.3 inches? Okay, so this one will be referring to the resolution in the display size, referring to PPI. Good. One moment, PPI. Okay, PPI. Pixel per inch. Okay, so perhaps you can take 2 minutes referring to the previous slide. Take 2 minutes to calculate this one. Printing resolution. Okay. Another thing would be something extra. If you, I mean, it's, if amount of you all diagnosed with COVID, please let me know. You can either WhatsApp me. You have a WhatsApp? Okay. Either you can email me or maybe Google chat me. Okay. So I will do a remark over there. Okay. Um, so far the policy is that anyone within the class, those that attend face to face, do have COVID, so should be quarantined for. I mean, cannot must be attend the online class for 2 weeks at least. Okay, and then yeah, if I'm the one who diagnosed with COVID, then of course we will go online. Okay, just for your informations. But whenever you have close contact or something change lah, either orange color, I think it's orange color or yellow color, or red color, which is you are diagnosed with COVID. So let me know. Okay. Or you can ask the course rep to let me know. It would be fine. Okay. Let us continue. Suppose you have a capture. Okay. Basically, this one is very simple. Maybe I mean, yeah, just look at it. You found very simple. So the resolutions horizontal and vertical, or horizontal and vertical. So basically, you divide by because I'm asking for PPI, the resolution, sorry, DPI, dot per pixel. So basically you divide 1200 divided by 4 and then 1600 divided by 5.3. You will get approximate lah, approximate to 300 DPI. Okay. Sometimes you will not get an integer lah, but you will need to upgrade it, round off it, or either round off. Another words, round off to the floor. How should I call it? It's okay. But anyhow, it's impossible because the DPI is per inch. Um, 1 inch, 1 inch. Okay. So it's not possible to have. It is a square. So for sure, within this square would be this is a total number of dot lah, within this square. So either 300 or 30 or 300, 301. Okay, it's impossible to have different number for horizontal and vertical. But of course, the resolution, the monitor itself will do some compensation in order to compensate, make sure both horizontal and vertical is 300 lah. Okay, they will do some minor discrepancy to auto correct this one by default. So that would be about the image quality, the image size, the size of the monitor, the resolution of the monitor, and also the number of pixel in your image. So it would decide the, I mean, what we learned just now, the previous subsections would be how you calculate the size, image size. Okay. So ability, now we focus, I mean, go into color visions. Ability of an organisms or machine to distinguish object based on wavelength or frequency of the light that they reflect, emit, or transmit. Okay, so this would be the basic principle, how human or any organism can see any color or object lah. Okay, basically the color that you are actually looking at. For example, you have a red apple. Actually, the red color is not the color of the apple, but the color rejected by the apple. Okay, I believe this statement is very, uh, I mean, is you all should know now. Already made known to you all during, I think physics, Form 5 physics or Form 6 physics, or maybe eventually Form 3 or Form 4 or Form 5. The physics is already state this principle. Okay, if you have looking into yellow balloon, yellow color is the color or the wavelength rejected by the balloon itself. That is why you can observe, I mean, you can see a yellow color. Okay, it is not the color displayed by the balloon, but in engineering term should be the wavelength rejected by the object. Okay, so when you see a white wall, so perhaps it absorbs everything but the white color. Okay, and etc. lah for black and etc. green color whatsoever. So basically, the way we can see color, we actually so-called see the wavelength. Okay, we are not seeing any color, but we see the wavelength. We respond towards the wavelength. So a person perception of color is a subjective process whereby the brain responds to the stimuli that are produced when incoming light react with several types of cone cell in the eye. Um, can I know how many of you do take biology or biology in Form 6 or maybe biology in Form 5? Anyone? Drop by of IO. Okay. All right. Form 5. Okay, good. Okay, because I found that many of, I mean, engineering students, they did not study biology. Lah. Okay. I think most of you study physics and chemistry, right? Um, oh, okay. But in Form 5, can you all drop biology? Possible? Okay. Because back to my time, I think for the science stream, maybe it's very dependent on the offer of, yeah, true, correct. Different school, different policy. Because my school, they want us compulsory, like I would say, for those science stream, you must take biology, physics, and chemistry. And because I'm from STPM student, so I take biology. I did not take physics actually. I did biology. So yeah, but I found that many of you have no biology background, which is very crucial, especially for those that join in medical image processing. Okay, if you're without biology background, sometimes you need to learn some basic anatomy, which is I think a 4 credit hour course. Uh, Purely like the medic students. Okay, so for those that are not, I mean, without the science background, I mean, the biology background. So perhaps you may not so understand the philosophy over here, like, especially in exploring the limitation of human being in terms of audio, color, yeah, both audio and color. Okay, so for this part, I mean, the subsequent part will be a bit relate to the biology part. So if you do not understand, please raise your hand or put in the chat box so that I can re-explain. Okay, this is my previous experience because after I explain, the student cannot understand at all because it's more to biology. Okay, a person perception of color is a subjective process whereby the brain responds to stimuli that are produced when incoming light react with several types of cone cell in the eye. So in our eye, this is your eye, your eyeball, something like this one. This is the lens. Sorry, the bad drawing. The retina. Mm, should be something like this one. Okay. So basically, when um when you the wavelength enter our eyes, okay, it will pass through the lens and then hit on the retina, and then in on the surface of the retina, I should use this one. On the surface of the retina, it has two different kind of cell, which is rod cell and also cone cell. Okay, cone cell is sensitive to color, and rod cell is sensitive to illuminations. Okay, so we actually reading now, just like a CMOS sensor or a color camera, we are actually reading the wavelength, and from the wavelength we reflect it. I mean, from the wavelength we can prescribe it or interpret the information of color. So visible color is an electromagnetic radiation with wavelength range between this one, 400 and 700 nanometer. So electromagnetic is another field. I will not say another field, but a field which is worthwhile to research. Okay, because EM is very important. Eventually, how the X-ray being formulate, CT scan, MRI, all involve the EM radiations. A light source emit light which contain EM. wave of many different wavelengths. So color is a sensation felt when this EM wave stimulate our eye. So this is your eye. This is the stimuli coming in. I mean the wavelength lah. Okay. So this all these wavelength we call as stimuli. And where is it? Stimuli. This one, stimuli. So we are actually reading this stimuli, and then we can interpret it, or also called we felt it as color lah. Okay, EM wave with different wavelength will produce a sensation of different color. Basically, you have higher wavelength in R, lower wavelength in G and B. Perhaps you will see it as a color. How does color blind occur? Okay, color blind, if not mistake, okay, because I've been, far a long time did not study biology. Um, Nevertheless, all these illness relevant to the color blind, and some other illness related to eye, is because some of the rod and cone cell is not functioning well. So when the rod and cone cell is not functioning well, which means you cannot prescribe the color accordingly. Okay, for example, you have a car park, but then the car park is being, car park is not a good example. Okay, you have a car, okay, but then the car is broken down. You still own a car, but a broken car. Can you understand the same thing? Okay, which means you have a car, you have rod cell and cone cell, but the rod cell and cone cell is not functioning as intended, something like that. Okay, so that would cause all this error. But in deep down, like the COVID-19, which antigen is causing this issue, then there would be a deeper knowledge over there to delve in. Okay, I hope this helped. So EM wave with different wavelength will produce a sensation of different color. So as I mentioned just now, if your wavelength consists a lot of R value, which is red color, a low value of green and blue, so perhaps you will see, so-called see this wavelength as red color. Okay, and the same apply to green and blue. So actually, for each and every color, we have a specific wavelength. So we call it as a spectrum of light. Okay. So basically, this is the visible light. So anything here and here, exiting this range, we will not able to see. For example, we cannot see ultraviolet, we cannot see X-ray, we cannot see gamma, we cannot see the radio wave and etc. Okay, but we can feel it. Not really that you walk into an X-ray room, and X-ray procedure conduct on you, and I feel the X-ray. No lah, not that feel I meant, but the feel is that you can so-called feel the X-ray or any other ray by looking into some condition. For example, when you expose to the ultraviolet ray for a long period of time, perhaps you might have sunburn, perhaps you might have the skin cancer, and X-ray is being used because X-ray is used to project to a specific location, for example, your lung. So some part of the body, for example, the bone is more solid. That is why the bone will reflect away the wavelength. So when the wavelength is being reflect away, so it will not display on the specific graphic paper or carbon paper. Okay, so that is how all these images, CT, MRI, and X-ray is being formed. Being created lah. Okay, the same to gamma. So gamma is very because the wavelength of gamma is very short, so the penetration power is very high. So you will be able, it's very easy for you to block the sunlight, right? Because within the sunlight, it consists of two different kind of light. Because you can see the sunlight, right? So it will consist of visible light and also ultraviolet. Because ultraviolet light is not so short, which means the penetration power is not so high. So perhaps sometimes you use some umbrella, black color umbrella, so-called the UV protection umbrella. It can reflect away the UV light because this thin sheet can reflect away the material, can reflect away the light. But when you use the same material to reflect away the gamma, is no way. Okay, so that is why you will always see the sign, X-ray room, and then or maybe MRI room, or maybe CT room. Then whenever they want to perform the MRI, CT, or eventually X-ray, they will exit the room, and then the light, the light beyond the door, X-ray will turn on, and then later on turn off, something like that. Because I mean, the main purpose is to alert people around there that now this area is radioactive. Okay, especially for MRI. So that is why during all those movie, you will see the patient, in a big donut, sat in the big donut, and then this is a room, and then the doctor will be always another room, observing this one, and then speak through the mic, and then ask the patient to leave his or her hand, and then take a deep breath and hold, something like that. So something Okay, something like that. So because this the wall over here is a thick concrete. Okay, yeah, it has to comply with certain ISO or certain safety guidelines or protocol, because only this type of wall can prevent the gamma ray from I mean penetrate through the wall and damage the doctor or eventually some other expertise over there. Okay, so that is why sometimes you go for CT or maybe MRI. It is suggested to have 6 months interval, because we still need I mean, maybe some of you would be curious, oh, then since this MRI and CT is very dangerous, why we still need to go for this CT and MRI diagnostic procedure? Because if without this one, you would be more dangerous. Okay, so when you compare both, you have to go for CT or MRI. Okay, because all these a radioactive particle, they have their half-life. I believe you all know about half-life, right? Since I think you all did took chemistry, half-life is something, yeah, half-life is the breakdown of half the value of the original radioactive, basically to determine the lifespan of a specific chemical or atoms, okay, radioactive atoms. So basically, it will suggest you only go for CT or MRI 6 months, one times per every 6 months, which means maximum 2 times per year. Okay, so this is some of the rules behind there. But since if the person, I mean, if the patient is very ill, then you have no choice. Okay. Anyhow, only long exposure to this gamma ray or any radioactive items would be dangerous, especially will trigger mutation. Okay, mutation is like the mutation here is not those like X-Men. After being mutate, you can shoot laser using your eye, not something like that. But perhaps you will have a very weird offspring. It will develop different kind of weird cancer and etc. Because in our human body, we actually have a gene which is when a specific gene being triggered or being mutate, it will cause different kind of cancer. Okay, so that is why all this radioactive is very I mean, the public has high concern for this radioactive. Okay, any radioactive material is top priority, priority in safety checklist. Okay, but anyhow, for the nuclear plant, it is very dangerous, yes, but also at the same time, it is very useful. It saves a lot of energy. I mean, it creates a lot of energy with very less input required. So, but of course, when there is a leakage from the nuclear plant, so it may cause many different issues, as per the Chernobyl, many other different, back to history, many different kind of these accidents occur. Okay. So the color of the light perceived depends on the wavelength composition. As I mentioned just now, it depends on the wavelength. So if you if you have a wavelength for something here, so you would expect red color. If you have a wavelength something here, so you would expect a green color and so forth. So a light source that contains EM radiations with wavelength around 700 nanometer will appear to our eye as red color. Okay, 700 red color. So check back to this one. I mean, the spectrum of light can be easily retrieved from internet lah. Okay. So table below shows the color of the visible light with respect to their wavelength and frequency. So basically, this table shows you the wavelength of the visible light: red, orange, yellow, da 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 da. Okay. You don't need to memorize this one. Okay, I would ask you, please state the wavelength of the of red color. Okay, I will not ask something like this one because I don't think this one contribute to the knowledge lah. Okay, so yeah, light is characterized by its spectral power density (SPD). So the SPD of a light is a function that defines the power of each wavelength in the light. So light with single wavelength is called monochromatic light. Actually, mono is one. Okay, di is two, and poly is many. I think this one is very common in biology. Okay, chromatic is referring to illuminations, light source. So this is part of the graph of the SPD. Basically, this is the intensity of a specific wavelength. Increasing. I mean, this wavelength is higher at this wavelength. The amplitude until here and there. So this is just example, okay, SPD graph. So like with a single wavelength, this is repetitive. I already removed this in your lecture notes in the Google Classroom. Don't worry. Color perception. The eye is like a camera. I would say the camera is like the eye, okay. But maybe some people not so familiar with the term. I mean, is much more familiar the camera rather than the eye, the structure of the eye. So perhaps this one, I'm not so agree lah. Okay, basically, camera is like the eye lah. Okay, the lens focus on the incoming light onto retina. Okay, basically the philosophy behind the camera. I mean, how the sensor being um the background of working theory um to interpret the wavelength and then from the interpret data to form the image is same as the eye as well. So the retina consists of two types of photoreceptor, cell called rods and cone. Okay, receptor is something that very common in biology, which is receiving something else. Maybe da 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 receptor depends on the words in front lah. But receptor itself is exactly receiving something else as per the original meaning. Okay, photo is relevant to light. Okay. The rod detect the light intensity and luminance and do not contribute much to color perception. So basically, rod is to understand the information of illumination. Illumination, which means it is bright or dark. This is called illumination. And the rod is sensitive to eh, sorry, and the cone is sensitive to color. Okay, so rod is only sensitive to light intensity. The light intensity here would be what I mentioned just now, bright red, dark red. Okay, but the rod is not sensitive to red, green, and blue. All these color, no. But that is the responsibility of cone cell. But so the cone cell will tell, oh, this is a red color, but the cone cell instead not really sure is it a bright red or a dark red or a maroon and what type of red is it, but the rod cell will tell this information. Okay, so the rod cell are more numerous, some 120 millions, and are more sensitive than the cone. However, they are not sensitive to color. However, the 6 to 7 million cones provide the eye color sensitivity. So based on these two number, it is obvious that our eye is very, very sensitive to light intensity, which means bright region, dark region, uh, and so on. But we are not so sensitive to color. Okay, because based on the number of cells, basically. There are three types of cone. So each type of cone is referring to one type of color, which is R, red, green, and blue. When hit by EM wave, cone cell label R, G, and B give response to the optic nerve. As a result, you see the light appear as red. So color perception is the result of combination response from the cone cell. So basically, the philosophy of each red cone, green cones, and blue cones is the same. Just that the intensity it fits into the nerve would result in different color. For example, um, you have a high trigger in red color, low trigger in green, low trigger in blue. So perhaps the cones will tell the nerve, oh, you have high portion in red, low portion in green, and low portion in blue. So perhaps this should be a red color or maybe red relevance image, or sorry, red relevant color lah. Okay, but this it, I mean, the decision here in is not decided by the nerve or neither by the cone or rod, but they are decided by the brain. Because this is a human eye. So after that, the human eye, eventually the human eye will send the information to our brain. So our brain will process this one and send back the information. So this is how it works lah. Okay, the nerve, I mean the retina, the corn cell, the rod cell is not doing anything in decision matter. Okay, it's only provide the information. Okay, so this is the basic structure of a human eye. So as you can see, the outside area, this one is the cornea, iris here, and this is aqueous humor. Aqueous is referring to sort of fluid, okay, fluid between these two regions. We call it aqueous humor, and the lens here, and the back part here is the retina. So this is the vitreous humor, this region, and fovea, this one. Fovea is not wrong. Fovea is the black uh, uh, black spot, right? Or blank spot. There's one word. What it is? Yeah, it's okay. And the optic nerves will be here. So basically, it will trigger dark spot. Dark spot. It's okay. Okay. Basically, it will after the cone cell or the rod cell detect the mm, intensity of light and also the intensity of a specific color. It will send through this nerve to our brain. Okay, and our brain will decide, oh, this is actually red color, or this is actually green or blue, and etc. Okay, so basically in our retina, we have two different kind of cell, which is a photoreceptor, which is rod cell and also cone. So rod cell is more on the light intensity, very sensitive and have abundance. But for the cornea, for the cone cell, you have maybe, less at least. And it has three different type of cone cell, the red, green, and blue cone cell. So it is actually red is sensitive to red color, green is sensitive to green color, and blue is sensitive to blue color. So basically, that is you are checking for something else. For example, you have a lot of you have one box of fruits, and then you have three siblings. The first sibling, he or she will check for apple. The second one check for orange. The third one check for banana. So the first one only check for orange. Only check for apple. The second one only check for orange, and so on. Only check for the banana. So for the same thing here, the red color corn cell only check for red color, and so for the green and blue. Basically, this is just for your information. Okay, the blue color here is the rod, the purple color here is the corn cell. And all these are on the retina only, okay, which is the back part of the eyeball. So diagram below shows the sensitivity of the cone as a function. So cone cell is sensitive to color as a function of EM radiation wavelength being plotted. So red, green, and blue. Human eye is more sensitive to green light. As why is sensitive to green light? Because this is what we plot lah. Afterwards, we have a higher level of higher intensity of relative rate response of green, and then followed by red, and then followed by blue. Okay, so this is the wavelength. I mean the wavelength here, the wavelength for red color, and the wavelength for blue color. And our eye is specifically more sensitive to green color and followed by red and then blue. So the red light is somewhat less sensitive than green. This is why blue region is so small. Okay, basically this one is a chart um, to check the response of a human. Okay, but I will not say this is applicable to all human being because some human may have different vision ability. So that is why this graph may not be true for everyone. Okay, we will learn another graph which is specifically to address the not common hearing capability of human being later on during the chapter regarding the audio processing. Okay, so for that one, it is a chart or an experiment. If not mistaken, it is carried out at Bell's Lab, which is the origin of Nokia. So that one is developed by two scientists, and it's actually collect the data on human hearing capability. But that one is not really, it would be a good benchmark because it recruit many participants inside the experiment, and then come up with a graph which specifically address the hearing capability of a normal human. Okay, but of course, when you grow older and older, perhaps your hearing capability would decrease, and so applicable and so the same to the vision graph. So when someone grow older and older, perhaps the sensitivity towards light, toward intensity would be different. So that is why this graph will be a very good benchmark, so-called the normal people. Okay, but it is not really true for each and every one. So three types of cone cell labeled RG and B cones, which they are highly sensitive to red, green, and blue. So light from the illuminance, which is this one, lambda, hit the surface of the object. The surface of the object poses surface spectral reflectance function as the absorb wave of certain wavelength and reflect the rest. So basically, this is exactly the same what we learned in physics during last time, perhaps Form 5. So as I mentioned before, when we saw a red apple and red apple, so the red apple is not it is not displaying the red color, but instead it is reflecting the red color with like away from the apple, but absorb the rest of the spectrum. Okay, so we are actually see the S function, which is a surface spectral reflectance. Okay, so basically a red apple will absorb all the other wavelength, but reflect away the red color. So when this reflect light, this is an apple, this is light source. Okay, of course you need light source in order to have the to see something. You must have a light source. So let's say the light source is from the sun. So the E lambda comes here and then hit on this object. This object will reflect the S function, and our eye, oh, and our eye can see this S function. Okay. So basically, this will be the function. So this is a light source. So release the EM, and then hit on this maybe green color pair, and then reflect. So reflect will be the Cm. Okay, this one times this one, you will get Cm. Okay, and then from this one, a human eye will, because we have rod, right? Rods and cones. So this one is for light intensity. This is for color, R, G, or B. Okay, so we need to combine all these value in order to know what color is it. So that is the basic philosophy of how human can see color. Okay, so basically this is it. Okay, RG and B. We know that the response from the three-cone cell allow us to see color. In order to respond or display the color, color has to precisely define. So how do we measure or define color? Describe color using SPD is not efficient because too many parameters. And especially when you do printing I'm not sure if you do have this experience when you have, for example, you have this green color. This is actually forest green. Actually, this green color display in different monitor would have different color. Okay, perhaps in my screen it was looks like a forest green. Of course, the color would be. I mean, the discrepancy of the color is not that big lah. It's impossible to have, you know, 它有 red color fonts, but later on display at your end, it is yellow color font. It's not possible lah. Maybe the red color is a bit different. Maybe I saw maroon, red, but in fact at your end you will saw a light color, light red, something like that. Okay, so this discrepancy is very dependent on the monitor, the capability of the monitor, the features of the monitor. How can you analyze a specific color? So let's say you cannot, you do not have so many color choices for you to display. Perhaps you will map to the nearest color. This would be sort of automation. I mean, by default of the monitor display setting. Okay, so the same thing, especially when you do printing. If you have this color, when you do printing, perhaps you will not able to get this color. Maybe you will get more to light blue color, something like that. So all this discrepancy, we need a specific code lah. Whenever when you want to print, especially your thesis later on. I'm not sure if you guys need to print the thesis, but if you need to print the thesis, the hardbound of the thesis, sometimes I mean, to be specific, you don't tell the shop that, oh, I want to print a blue hardbound, because blue hardbound, there is a lot of different kind of blue. Usually you will use a color code. So the color code will be sort of not really layman terms, but it is not so professional as well, because it's impossible for you to I mean, mention a specific color using the SPD. So instead, usually people will mention the color using the color code. Okay. So chromatic theory say that we can see different color by mixing or adding three primary color source, which is RGB. So color can be defined by specifying the proportion of mixture of three primary source in order to match the desired color. Okay. So basically, you have as I mentioned before, you have R, G, and B, and for each of it, you have 0 to 255. Same thing. So in order to specify a color, perhaps you need to tell what is the color uh, intensity for this one. For example, I have a red color. Red color can have maybe, because it is red color, for sure the proportion of red would be very high, 200. But if you have a 0, I mean 0 green and 0 blue, perhaps this red color is very dark red. Why? Because approaching to 0 is black color, which is nothing. So for this one, you will expect a very red color and it is not so bright. Okay, so something like that. So if you have 200, 200, 200, so this is exactly the grayscale. Okay, because in grayscale, when you process using your MATLAB, it is actually sometimes when you click into the grayscale image, it will provide you sort of RGB value. But the RGB value is the same in text. For example, 100, 100, 100, something like that. Whenever you click another button, another pixel, 2, 2, 2, maybe 46, 46, 46. Because when all these, RG and B have the same value, it is actually equivalent to grayscale. Okay, but it depends again. It is depends on how you store the image. For example, you can display the same grayscale image. Let's say you have a grayscale, maybe okay, and you have a color image. Because grayscale only got one bit, right? Sorry, 8 bit, right? Which means only one slide. So perhaps this one is 140. So if you have another color image, and then you set all the pixel within this image to become RGB 140, 140, and 140. The outlook of this image is the same, exactly the same as this one, but in fact it is using 24-bit, but this is using only 8-bit. Okay, the same thing. If you have a black and white image, binary image, if you have a grayscale image, but the black and white image you only have, this is black color, the background is white color, and then you have another grayscale image, the same thing. So this is all the pixel within this one is 0, all the pixel at the background is 255. You will have the same thing, display the same thing, but in fact this is 8-bit, this is 1-bit. So that would be the difference. So we always want to, in chapter 1, we always say that it is depends on the application. Yes, it is always true. Because in multimedia application, you will want to look into your application to consider what is the best solutions. Because we cannot say that JPEG is the best, or maybe BMP is the best, or maybe TIFF is the best. Actually, it's very dependent on your application. Let's say you want to store image, and the image features, the texture, the fine texture in the image is not so crucial to you, then perhaps you can use JPEG. Because JPEG is sort of, by default, it will compress the image, and of course, it will return a small image size with acceptable quality. Okay, but in fact, you want to do further processing, then you don't want to use a JPEG image, because whenever you use a JPEG image, the image information will be removed automatically. So you may lose some of the important features in your input image. But let's say you want to do what else? Yeah, something like that lah. Okay, it's very dependent on your applications. Okay, so that's all for chapter 2. Any question from you all? No? Okay. That's good. Then we can have a 5-minute breaks, and then we will start chapter 3. Okay? 5 minutes breaks. Okay, let us continue. Okay, for this chapter, we are actually looking into color in image and video. Okay, color in image and video. So basically, we will learn more in terms of color perceptions, how we actually see color, what color is, um, it's very vague for us to say all color, but actually what color it is. The very common color would be RGB, right? But actually there is some other color, for example, CMYK, many different color model, I would say. Um, the basic one, for this, because we only have like 15 minutes left, perhaps I will give you all introductions to this um, chapter. Okay, so basically we have very, different color model. For example, RGB, CMYK, HSI. So basically, all these refer to different things like, for example, YUV, YIQ, YCBCR, different color. Again, there is no best color model that could be used, but instead it is dependent on your application. So, for example, like normal display, especially during the monitor display, on-screen digital screen displays, but as we opt for the RGB. But when we go for uh, printing material like printing shop, poster, and etc., we will go for CMYK. Okay. Um, RGB will be primary color, CMYK will be secondary color. I will explain more on this later on. And HSI is more to hue, saturation, and intensity. Q would be the HSI is very close to what we can see because hue is actually relevant to the color uh, that is displayed by any screen or any wavelength that our eye can see. And then later on, YUE, YIQ, and YCBCI is more on video. Because for different model, different application like image and video, we need different protocol or different standard to um, to perform the not to perform but to ensure a very smooth transition of color from one image to another image, from one pixel to another pixel. And this transition of color, and who would decide this is not it's actually a group of people lah. For example, like a JPEG is a group of committee which decide, oh, we use JPEG and how what level of degree we are using in the algorithm, what algorithm behind we should use, something like that, and how many pixel block we need to partition into, something like that. So the same thing here. Different regions, for example, Europe country, Taiwan, China, Malaysia, Asians, different country or different region, they would have their very different protocol to display a specific image or display the video, especially for video lah. Okay, because video image is quite individual, I would say, because you don't need a common channel to display the uh, image. But for TV, perhaps you need to standardize between across the country. Okay, because you are receiving the same radio wave from a specific satellite and etc. Okay, so basically in this chapter, we will learn how human eyes see color and how the color is being calculated. I would say quantitatively, because you will need to calculate the color. Okay. Let us go to the first sections, color model. So color need to be defined to facilitate color processing and display by computer. To define something else is very important. When it comes to define, which means we brings everything to quantitative. Okay, not qualitative. Qualitative is like red. How red is red? This is always the question for qualitative. And to quantitative, oh, the RGB intensity is 200 100 100. Okay, so this would be quantitative, which means when we comes to the words quantitative, we always refer to value lah. Okay, values or something measurable. Okay, so color definition means to assign a three tuplets value or number or color coordinates based on a model to represent a set of color. So color can be defined by choosing three primary color, P1, P2, P3 for red, green, and blue respectively, where R, G, and B is the mixing rate. Basically, the first one is referring to red, second one is referring to the green, and third one is referring to blue. But R, G, and B is the intensity. For example, uh, this one, 200 R, 100 green, 100 blue, the same thing. So you add up this one. Of course, this is not you don't see this as a mathematical equation. What I mean by add up this one is 200 in first layer, 100 in second layer, and 100 in the third layer. And when you combine this, you see this as red color with a specific red. Okay, not a random red, but a specific red color. Okay, this is not simply add on everything 200 plus 100 plus 100, so you get 400. No, not something like this one. Okay, don't misunderstand. So the combination of three primary color, which is red, green, and blue, will produce a wide range of spectrums. As I mentioned, how many color you can produce, which is 256 times 256 times 256. Let me check what is it, 256 power 3. It's up to 60 million. Okay. Color model, color space, a color system, color scheme provide standard approach to define color. So basically all these words might be not so common to you all, but color model, space, system, scheme is synonym lah. So you wouldn't expect to have, it's different. It depends on the reference book lah, because sometimes some reference book use color model, but some use color system, some use color scheme, and etc. But it is actually referring to the same thing. Okay, you don't have a specific terms for this one, but in this lecture, I usually use color model. Okay. But nevertheless, color space, color system, and etc. is not wrong. No such thing wrong. Just that different context, but it's referring to the same thing. It's provide the coordinate system which each color is defined by three tuplets number. Three tuplets number, which means RGB lah. 1, 2, 3. Okay. Gamut is the range of color that can be produced by the color model or generated by a specific device. It describes the range of color that can be produced by combining a set of primary color. So basically RGB is known as primary color. RGB primary values are three cones. The secondary color CMY, sorry, are at other corner. So this one will be illustrated later on. So cyan, magenta, and yellow are different color, but we call it a secondary color. Okay. Um, Again, it don't have. We don't have any superior color or whatsoever. Eventually, for primary and secondary, we don't have any superior color model here in, but rather we want to look into different contexts or different I would say application. Okay, we are heavily dependent on the applications. Some applications Cmyk display so well, but some application RGB display better, and some application we prefer HSI. Okay. So K is another is at the origin and white at the corner far away from the origin. Just for your information, Cmyk is another model, which is cyan, magenta, yellow, and K is referring to black because we don't want to confuse it with B, which is blue. So we use a K. But initially, you may, in some application, you may see CMY only, but not CMYK. Why? Because actually, the secondary color is only involves CMY only. I mean, the secondary color only involves CMY. K is added on later on. Why K is being added on? Because CMYK is usually used in the printing industry. So basically, everything. you have 0 to 255, right? When everything, when you have a maximum value, 255, 255, and 255, you will get a white color. If you have 0, 0, 0, you would get a black color. But in real life application, when you assign 0 to cyan, 0 to magenta, and 0 to yellow, you will not get a pure black color. That is why most of the color is not pure. It's not pure in in nature. So that is why because everything we mentioned here would be ideally, but in real world application, it's hardly to have a pure color. I mean, pure red, pure blue, and pure green. Same apply to cyan, magenta, and yellow. But black color is always being used in printing industry because all the fonts, all the writing, or maybe some heading or the outline of the graphics are in black color. So black is very important and something always in use in printing industry. So rather than, because when we assign 0, 0, 0 to cyan, magenta, and yellow, which is secondary color, you will never get a pure color, a pure black color. So that is why uh, I mean instead of wasting your time to mix the value of cyan, magenta, and yellow, CMY, so the industry decide to add in another color, which is black color. So black color is a pure black color and always being used in the printing industry. So that is why when we deal with the printing industry, we always have CMYK. But when we talk about secondary color or maybe some application that only needs the CMY, we will only pronounce CMY. Without the K value lah. Okay. So that is the reason why later on we have CMYK instead of CMY. Okay. But in some extent you cannot see CMYK lah. Okay. So you have to know the reason why K is over there. Okay. Okay, so this is the so-called three tuplets of color involving the primary and also secondary color. So this is the primary color, red, green, and blue, and um, s- this is the secondary color. Let me use this one. This is the secondary color, and when everything becomes 255, you will 255, you will get a white color, and everything becomes 0, you will get a black color. Okay. So this color box, the coordinate here shows the relationship between these two. So basically, you have three exit, which is a 3D block, the red, green, and blue. Okay. Red, green, and blue. So for this one, we only, this is, the value here is being normalized, which means 0 to 1 only. And the value between will be 0, the range 0 to 1, 1. Okay, so when you have a pure red color, you will fall into this line. When you have a pure green color, you will fall into this line. The bracket refrain red, green, blue. Okay, and when you have a pure blue, you will have fall into this line. And when you have one of the blue and one of the red color, which is uh, red and blue color, you will become magenta. And when you have green and blue, you will get cyan. When you have red and green, you will have yellow. And you have everything one, between 1, 1, 1. As I mentioned just now, 255, 255, and 255. Because after you normalize this one, it's become 1, 1, 1. You will get black. Sorry, white. And when you convert it everything to become 0, you will get black color, which is the origin. And any value from this line, black to white is considered as grayscale. Okay, so actually this block summarize primary color, secondary color, white, black, and also grayscale color. Okay, so always remember for this one, for this graph, it is already normalized. The value is between 0 to 1. Okay, How to normalize? Basically, you divide by the maximum value. I mean, in any context, to normalize something else, you divide by the maximum value you have. That would be the main so-called normalizations. And in our context, the maximum value is 255. So basically, we divide everything by 255. For example, 100, 211, maybe 170 divided by 255, you will get a normalized value which is between 0 and 1. The same thing. Okay. So any questions so far? No. Okay. If none, so I think no question. Okay. If none, so that's all for today. And one reminder to do the tutorial. We have tutorial for both the class, 16 students and so the 14 students together online this Thursday. Yeah, I will send a reminder in the Google Classroom for both the groups later on, maybe one day before. Okay. Make sure you do the tutorial because for tutorial, perhaps I will randomly ask one of you to share your screen and share your answer. Okay. You can share your answer in the chat box or either share screen, either way. Okay. So that is how tutorial being conducted. Any more questions? On the count of three, three, two, one. Okay. So that's all for today. Thank you so much. Thank you everyone. Bye bye.